All right, I hope you are ready for example number 3 of our related rates question. This one is about a balloon flying up into the air. So a small balloon is released at a point 150 feet away from an observer who is on level ground. If the balloon goes straight up at the rate of 8 feet per second, how fast is the distance from the observer to the balloon increasing when the balloon is 50 feet high? So take a sec to reread this to yourself. Make sure that you understand the situation. Because ultimately, you'll have to be okay at translating these things on your own. So I would say this situation really warrants a good drawing. Yeah, you can even label, like we've got some ground, right? We've got a balloon that's rising up into the air. So you can draw the balloon maybe like here. We have an observer who is on level ground from where it was released. So someone's watching from afar. So maybe, here's that person. We know that the balloon is going up at a rate of 8 feet per second. So here's how you might label that. And we want to know how fast the distance from the observer to the balloon is increasing when the balloon is 50 feet high. So the distance from the observer to the balloon is like this, basically. We want to know how fast that's changing, right? As the balloon goes up, maybe the balloon's up here, then this is a longer distance, right? When the balloon was down here, it was a shorter distance. And so this distance between the observer and the balloon is in fact changing. It's getting larger as the balloon rises up. We want to know at the point in time when the balloon is 50 feet high, what is that rate of change? So we also have this distance that we need to get involved. Okay, so maybe we'll make that distance there. Oh, and there's one thing that we didn't label in here, that the 150 feet away was the observer. Now, we have this 50 feet here. We have this 150 feet here. Oh, iPad, come on. Been doing so good today. Oh, okay, all at once. Not what I was trying to do. So we've got 50 feet here and 150 feet here. Now these are different because the 150 feet, this is not changing, right? The person isn't moving from where they are, and the balloon is released and going straight up. It's not moving towards the person or away from the person. That would actually add a layer of complication to this that we're just not going to worry about. However, the 50 here, this is changing. So we want to not label this as 50. We want to actually label this length as a variable that's changing, but we can label this as 150 because this is constantly the same at 150. This is a constant. Okay, but again, over time, this length is of course getting larger and this length is getting larger, but this 150 is always staying the same. So we want to include some variables in here. You can use whatever you'd like. We usually have like X for horizontal and Y for vertical. So I'm just going to use a Y here for that length. And then this diagonal one, I'm going to use a Z for that length. And again, we could call this X here, but this is always 150, so we're just going to leave it as 150. We don't even have to label it as a variable. Okay, so let's start making like a know and want column. So the knowns or the givens let's put some labels onto things using the way that we've labeled our diagram. So I think that this 150 is taken care of in our diagram. We don't need to worry about that. It says if the balloon goes straight up at the rate of 8 feet per second. Okay, let's just stop there. So we put that here, but what is this in symbols? Right, this is related to this distance that we're calling y. So this is the rate of change of y. It's telling you how y is increasing. Well, it's getting larger at a rate of 8 feet per second. So this tells us that dy dt equals 8 feet per second. Okay, then after the comment it says, how fast is the distance from the observer to the balloon increasing? Okay, so that's this. How fast is the distance increasing? That means rate, right? How fast, increasing, those are all rate words. So that means that we're looking for the rate of change of the diagonal distance of z. Okay, so we want dz dt. That's what we're looking for when the balloon is 50 feet high. So that's when this length, y, equals 50. At that point in time when y is 50. All right, so we need a relationship that is going to relate the distances of 150 here, y and z. Now, if you look back at the formulas that I gave you on the first page of these problems, there are two there that involve triangles. One of them is the area of a triangle. That's not what we're looking for. The other one relates to distances or the lengths or the legs of a triangle for a right triangle. We actually do have a right triangle here. And so we are going to need the Pythagorean theorem that will relate the three sides that we've got. Okay, so Pythagorean theorem says, well, it would be a squared, 150, plus b squared, y, equals z squared, or c squared. All right, so we'll have 150 squared plus y squared is equal to z squared. Okay, so this is the equation that relates the quantities of the lengths. Now we want an equation that relates the rates of change of these lengths. And we can find that by differentiating this equation from the Pythagorean theorem implicitly. Okay, so let's differentiate implicitly with respect to time t. Okay, so in the first piece here, we will differentiate the 150 squared. That's a constant, so that just differentiates to 0. I didn't square it out because I knew we were going to do that and I didn't see a point. That's just going to go away when we get our rates. When we differentiate y squared, we'll get 2y times dy dt. And then when we differentiate z squared, we'll get 2z times dz dt. So in other words, we have 2y times dy dt equals 2z times dz dt. And here's our equation that relates the rates. If you wanted to, we could divide by 2 on both sides. That'll just simplify a little bit. Make our numbers a little bit smaller. So we just have y dy dt equals z dz dt. Okay, so now we can start plugging some things in. So we know that dy dt is equal to 8. So let's start substituting some stuff in here. So let's substitute. Right, we know dy dt is 8, so I'm just going to plug in an 8 right here in the dy dt slot. We want dz dt when y is 50, so I'm going to put a 50 in for y here. I'm looking for dz dt. So I need to have a value for z in order to solve for this. Unfortunately, I don't have that listed anywhere. So sometimes you have to go back and think a little bit, find the value of one of the three sides if you know the other two. So we actually have enough information about the triangle when y is 50. We know this side is 150. And so we can find at that point in time, what is the value of z? What is the length of the hypotenuse? Okay, so we need to find the value of z now that goes with y equals 50. All right, so let's just make a note of that because we'll do it off on the other side. We need to find z when y equals 50. Let's do the work over here. Okay, so I know the equation that relates the actual values of y and z are here, or is here, the equation 150 squared plus y squared equals z squared. So let's put in 50 for y. So let's see, 150 squared is 22,500. Let's add 50 squared. So it'll give us 25,000. And the way to solve for z here will be by taking the square root of 25,000. And that comes out to be about 158.11. So let's just leave it like that. So say z, we would get plus and minus when we apply the square root, but we don't need the negative value. We can just take the positive one because z is length. So let's say z is about 158.11. So now we can plug that into our equation. All right, so in the end, in order to solve this for dz dt, we'll just divide both sides by 158.11, or more exactly, the square root of 25,000. Okay, so we'll get, let's see, 50 times 8 is 400. So I'm just solving for dz dt here. So I'll just divide this to both sides. Over here we have 400, so that's 400 over 158.11. So 400 divided by, again, more exactly would be the square root of 25,000. And that comes out to be about 2.53. 2.53. So the units for this, the measure of z is a length measuring in feet, and the time is in seconds, so this would be feet per second. Okay, in our next example, we are going to look at a cylindrical shape, or a coffee mug. So tune into that, and I will see you then.